All right, so long, right? uh, this is our session about fleet memory fault management. Again, I'm Yogesh Varma. I'm from Intel, joined with Drew Walton here. Um, so, like I said, this work stream is spawned from the hardware fault management subproject, and the focus is on developing a framework for fleet memory fault management, and that's subset of or part of the hardware fault management requirements framework. And we have two very simple goals. First one is to increase the fleet memory error handling precision, and what we mean by that is don't have false alarms, don't do returns just because you didn't know better, right? So we're trying to get to the point where we can precisely identify where the fault is. Is it a CPU, or it's a DRAM, or is there a RAS section possible? And second is, with the help of standardization, we want to simplify the adoption of RAS features for memory in the large-scale fleets, right? And our method is to standardize logging, error formats. What I mean by that is what to log, how to log it, what interfaces are used. So we're trying to abstract things out, but in a way that we still preserve the innovation. So individual DRAM vendors, which are present in this sub-project, can continue to do their innovation, but at the same time provide get the error logs, provide us analysis tools, and provide us feedback on what transactions are needed. Like I said, we are very well attended by all the DRAM vendors, all major OEMs, and silicon vendors, CSPs alike. So very happy to have the participation here. And we are joined in the room by Paul Fahey, and thank you, Paul, and Roy Chung for providing. We try to create some consensus and get their views, like why we should do this and what needs to be done. And like you say, you see, SK Hynix very clearly underscores the need for improvements in the managing of the DRAM field quality. What is meant by that is that when the memory is deployed in large fleets, there are a lot of opportunities to approach the errors from the platform view, get the error logging from platform, and provide the RAS section as a return to the platforms. And in support of FMFM, which, thank you, Paul and Roy and everyone else from your company for attending this work stream very regularly. They believe that these activities will enable them to realize the most promising methods for avoiding memory-related system crashes. So that's a statement from SK Hynix. And we're also joined in room by Tony Giddle, Evan Pearson, and their colleagues, and they state that Micron is committed to the standardization of memory fault management because they see value in scalable and proactive solutions that can come out of it, which will lead to reduction and remediation of faults in the fleet scale application. And they support aligning on standards for with the rest of the industry because it provides maximum value to the customers and leads to improved uptime and reduced maintenance costs. And the data that gets generated helps them improve their internal methods for quality improvement and RAS actions that can be taken. Finally, thank you, Jongmin and their colleagues from Samsung. They think FMFM has significant impact on users, memory subsystem architects, and the memory manufacturers alike, because they believe that it provides visibility into early life failures and also creates a closed loop to for continuous and long-term improvements in the memory RAS, right? They also believe the system for system architects is pivotal and innovative, because it helps them integrate fault analyzer that can help validate memory, system, and SoC implementations. And finally, for the end users, these activities are future of the industry and provide a total solution in terms of driving near-term and long-term improvements in platform uptime and availability. So I feel pretty good about this, that all the major DRAM vendors are coming together and working with major, silicon vendors and CSPs, and we are very happy and we have high hopes from this work stream. With that, it's time for some CSP view. I hand it over to Drew.
Thank you. So, if you think about what's in a data center, a large part of that silicon is memory. And memory failures can have a gigantic effect on the reliability of our machines. So this is really important. And we did an internal evaluation where we said, okay, what happens if we count memory errors? So let's just say we count corrected memory errors, and when we see X in a certain amount of time, how good is that at predicting a crash? Because let's face it, at the end of the day, if the machine is correcting an error, it's not crashing, the corrected errors aren't causing a performance problem, why am I replacing the part? I really want to replace a part when it's going to cause me to crash or when it's going to cause me to have a performance problem. We found that counting memory errors generated an enormous number of false positives where we returned the part and there was no discernible problem. We found that we saw a 0.6% precision. So that's not 60%, it's 0.6. Let me put that in perspective. I am convinced that if you saw a corrected memory error and you flipped a coin, you get 3 orders of improvement in precision over counting corrected memory errors. Now, let's think about why that is. And I think Roy, I see a little grin on Roy's face. He's been telling me this for years. I believe you, Roy. And our numbers verify this. But the deal is that if you count errors, the error detection in the system is entirely dependent on whatever your software was accessing. So if you access a stuck cell in memory, you can drive any memory counter to any value you want. And sometimes software does that. So counting corrected errors weighs a single stuck cell in the DRAM, which, by the way, the error correction codes in the CPU will correct indefinitely, like for years, forever. It weighs that the same as a rank is failing and I'm getting a boatload of corrected errors and I'm about to crash. So you have a wildly different scope of damage and you have a variable that doesn't allow you to distinguish between the two of them. So the answer is to look at patterns, figure out what those patterns mean, and figure out what is failing inside the DRAM, and then weigh that against the CPU's ECC. That will enable us to say, does this pose a risk of crashing? Now the problem is that we don't know how to do that. So we are working with the memory vendors to get the error logs that we need and rely on their understanding. And each DRAM vendor has a different architecture and do different things, and failures manifest themselves differently. So we're relying on them to help us figure that out and then only replace memory that's causing crashes or causing a performance problem. And to do this, we have a whole bunch of activities in place. We have the overall framework that we showed you in the previous presentation, and what we're doing is we're plugging the tool that the memory vendors are providing into the CPU vendors analyzer. And the reason it's the CPU vendors, they own the memory controller. So we have to weigh their ECC against what's going on inside the DRAM. We're building a standard format just to figure out what errors we need. We're figuring out what the sampling rate is and what the overwrite rules and what the priorities are for different types of errors. And then we're establishing basic requirements for a memory analyzer because we know they need to take certain data in, and they may come to different conclusions, and we need a way to express those conclusions to the CPU vendor so they can then say, how does this affect my ECC? So we've got to put all that plumbing in place. And in the end, we're going to have a message that says, hey, you've got a row failure. Let's do a post-package repair on the next boot. And so then we have to abstract those to enable the tools to work uniformly across our fleet, across vendors. but in a way that the vendors can do interesting things. So, if one of the memory vendors comes up with a better way to organize memory, it'll work because they provide the analyzer for their tool. But it's uniform to us. It's just a piece of software we plug in. And so our goal is to contribute these requirements for the OCP 2024 Summit, and we're building proofs of concept. We're doing some experiments. We hope to have some actual numbers to share with you. And so you can kind of see how this fits in the overall framework. Bullet number 1, you see that we're using the memory vendor's knowledge of their failures, or their DRAM designs, to characterize failures. We're working with the CPU vendors to characterize ECC. We're gathering the data in a common platform error record, CPER, that is opaque. So if they're worried about IP, it's a binary format, and we don't really care. The binary format bubbles up through our infrastructure, then it goes to the analyzer, which then can decode it, analyze it, and tell us what's going on. It enables us to figure out exactly what's broken, when we're going to crash, and it allows us to automate RAS actions. And so you can see the structure of the memory vendor specific analyzer. And so we're trying to stitch a lot of things together. And so this is something of a work in progress, but we know that we're going to log errors, we're going to decode them, we're going to have a DRAM view of things, we're going to have a platform view of things from the CPU vendors, and then we've got to figure out, okay, it's a bad row, or it's a bad column, or it's a bad bank. What do we do about it? And sometimes the memory vendors have been encouraging me to say, hey, how much memory can you really lose? Because maybe you can map some bad pages out in the kernel. We don't really have a framework for evaluating whether that's going to work or not. With their help, we can do things like that and invest in those features with confidence, because the people that designed the chip are helping us figure out that it's an appropriate action. That gives me the confidence to say, okay, we can invest in this. And then, of course, at the end, we send actions back to the platform. So the call to action is, come join us. And just, I get up at 4:30 a.m. on Tuesdays to be at work in time to join this meeting. And it is worth every bit of pain that is involved for me opening my eyelids that early, because it's a great group of people, the meetings are productive, we're figuring things out, and we would like you to join us if you're interested in making memory work better. So please come join us. We would love to have you.
So like you saw, we have a goal to contribute the requirements for FMFM, which is memory handling at fleet scale. So yeah, welcome to join you all. Now, we have time for some questions, right?
Hey, thank you. Quick question. So on one side, we have the hardware behavior. We're trying to standardize that. On the other end, we're trying to standardize the abstraction layer, the utilities like FMFM or RAS or Redfish or what have you. What about the middle layer, right? Where if you have certain hardware and that is controlled by BIOS or other firmware, and that responsible contributor is not part of OCP, how do we control the behavior of said hardware then? For example, if in a server board you have missing DIMMs or fully populated DIMMs, or all DIMMs are missing, hypothetically, right? How do we control the behavior of that? So that's, I believe, controlled by the BIOS. If the vendor is not part of OCP, how do we then control the end-to-end workflow?
Well, I guess the way I would characterize that is that, if you don't mind, Yogesh, when a memory fails post, we know it. I mean, the BDAT tells us, it's pretty obvious to us that the memory failed. Now, it may be that if all the memory failed, the system can't boot. That's where the out-of-band logging comes, and we'd see that. But to be honest with you, if memory fails at boot time, that's actually not a bad time, because it's not running a customer workload. There's probably someone that just racked it, and there's a technician at the machine because they just put it in and it's just coming up. So we haven't lost that much, and it's not that hard to figure out. The the BIOS is telling us a DIMM is bad, and the BIOS knows how to express that. I think that the problem we're trying to tackle is a bit more difficult, because what we find is that memory failures are pattern sensitive, and the things that I've been on one machine where we built the firmware, we built the chip, we built the memory controller, we owned it all. We thought we had it right. We booted, and the OS promptly crashed because the memory was tragically bad, but it passed all of our self-tests. So now, that again was actually pretty obvious in the end, but my point is that boot time is one thing. It's a little easier to deal with. Runtime, there are pattern sensitivities, and like when we booted that machine, there were OS pattern sensitivities that broke our memory subsystem. And with smaller DIMM feature sizes, those patterns are maybe harder to find, but more numerous. And so that's really our value here, is more like runtime monitoring.
Since we have a lot of time, I have two questions, if you don't mind. First one is, you were saying what I interpreted as single-bit errors don't always lead to a double-bit error.
That's correct.
And we need to count unique single-bit errors. Did I get that correct?
So what I didn't say what we need to count.
Yeah,
I'm looking over at my memory colleagues here for them to tell us what to count. I'm going to be super careful there. But what I would say is single bit errors can be corrected indefinitely, and there's such a thing as a weak cell. I mean, and I'm not saying that because I see the Micron guys nodding. I think the other memory folks would nod that they're weak cells and they're isolated.
Okay, next question. Is there any plans to expand the work group to include on-die caches? Because we have the same challenge with on-die, large caches on the die.
I'm going to defer to my
we
Intel
want to,
colleague.
kind of follow Amdahl's law here, right? So most prominent and most common pain point is the DRAM, and the biggest source of errors, most expensive item in the server. That's what we want to go after first. And yes, we do plan to expand the scope, which things we haven't decided that quite yet. HBM could be one of the things, that is integrated on various silicons that could. So there are other things which we can go after, but I think first things first, right?
I assumed HBM was included, but okay, maybe HBM first before on-die cache.
DDR first.
Yeah, I just have one question. For expanded memories using CXL, are we addressing in the same work stream or for the new framework which may be required here? In this case, we are bringing PCIe and DIMMs together, and for the new challenges, do we have a separate work stream, or is there a scope for this work stream?
Are you motivated enough to go after that?
Yeah, of course.
Yes, so there's, like I said, it's a small group of people. We have our energy directed right now at DDR. CXL is definitely going to be next big use case, and CXL has its own ecosystem. Memory controllers are distributed too, and kind of specification is still nascent stage. They're still making changes. Things are evolving. So there's a lot that we will see changing, and of course the PCI .io protocol is there in the picture too. So there are a lot of complexities there to handle. But yes, I think that's something that as an industry we need to go after next. When the adoption increases, I think that will become a very compelling subsystem in this server to go after.
Well, and if I could add something, so let's say I make a CXL expander for the area I'm working on. I know what's going on here. I'm going to tell them, log the data. And if I can log the data, I can send it to the analyzer. So I think at the end of the day, the key for this here, now maybe at some point, the RAS API, in my dreams, the RAS API we're going to talk about later will be so ubiquitous that it'll just be there on the CXL devices and we'll get the error logs. I think the key though is that what we're doing here is all about collect the right data, however you can, send it to these analyzers, and these analyzers tell you the right thing. And it's less about the plumbing, but I think that other work streams within the hardware fault management will add the plumbing. We're just treating the data collection and analysis separate from the plumbing to connect the two.
By the way, I don't mean it in a mean way. I really welcome and would like you to join our efforts. It's beautiful, it's very nice, 7 a.m. in the morning, lovely time to.
Absolutely, I totally appreciate all your efforts. Thank you.
Okay, so I just want to follow up on the question you asked. So this is a real problem, the boot time memory failure detection. And right now in the industry, there is no standard way of detecting, reporting, and then deciding what action to take. So there is a room to bring that into OCP community. And in fact, the overall arching, the sub-project, which is where we call hardware fault management sub-project, we are kind of keeping it very flexible and very open. And within that umbrella, there is an opportunity for us to work on that also. We are not started yet, but there's a
Absolutely, I agree with you 100%. You know, and so my answer was strictly for what we're doing here.
Yeah, we will. It's just a matter of, yes, Yogesh was saying, right, we have only few people, right? So we are kind of taking one thing.
Yeah,
We're
that-
triaging.
that is a real problem too, right? We have, like you saw, a list of things, and you know how, and you know, John here doesn't help. He wants us to do things like this.
Right now in Meta, we are actually working with every vendor to solve this problem one at a time. And the solution we are putting together is almost standard based now. So, but we'll get it to the CP also, yeah.
We are not going anywhere, by the way. We are adding to the strength.